So welcome to this lecture 9, and in this lecture we will see the concept of complex power, and this complex power appears in AC circuit because of the fact that we are now representing this time domain, that is voltage and currents are sinusoidal. So this sinusoidal quantities, if you remember in previous lectures, they are represented in form of phasors. So phasors are basically having angle and magnitude. So it can be represented as a complex number. We have seen that way, and once we have complex numbers in terms of voltage and current in terms of complex number, obviously the power, when we try to see power, it also becomes complex. So that is how complex power having complex values would be appearing in AC circuit. This is characteristic of AC circuit because when you represent those time domain values into phasor domain, then it actually becomes complex values, and the power also comes out to be complex. So here if you see, this is V. If you remember root 2 V RMS sine omega t, this is represented in time domain, and similarly this is I. And let us see, this is the circuit we are talking about, where you have some impedance, and impedance would obviously in a form of something like this, which we have already seen. The impedance comes now in AC circuit, they come in this flavor, that is ZL plus. ZL is also complex, so impedances also becomes complex. So when we represent this voltage and currents in phasor forms, okay, then we write complex power as we do in case of DC circuit. We multiply voltages and current VI into V into I star. So it is common to multiply to take conjugate of that. So VI conjugate is now the complex power we can calculate. So let us see, if we represent Vt and It in a complex form, or in a phasor form rather, and then we try to calculate Vi conjugate, then let us see what do we get. So if this is Vrms theta V, that is angle of voltage, and Irms angle of current theta I, and when we multiply them, obviously you are taking conjugate, that's why this is getting subtracted, and these two values are multiplied. So this is basically phasor multiplication of two quantities. So these two phasor quantities are multiplied, and then you represent them in a you can say rectangular form. So phasor form to rectangular form, and this is basically also called polar form, and this is called rectangular form. So in rectangular form, if you see, same thing, VI RMS cosine part, that is the real part, and this is J times RMS IMS, so this is the imaginary part. So this is how the power appears to be when you multiply them, and this power when you multiply V and I is also complex, and that can be represented in form of P plus JQ. So this is the real part, and this is the imaginary part, so to say, but we don't call it imaginary. This real part is obviously called as real power, but this imaginary power, it is practiced because saying imaginary power really appears that something imaginary is happening, whereas it's not so. So that part is called the reactive part or the reactive power. So this power S can be represented as real power, that is the real part, and the reactive power, which is the imaginary part. Okay, real part of S and imaginary part of S. So now let us, there are now three powers, in fact, S, P and Q. Okay, three kinds of power we are seeing in a AC circuit. Let us try to name them. What are these powers actually? So if you see this, we call S, that is multiplication of Vrms into Irms. Okay, so if you see here, this part and this part, this phasor form is there, but this has a value, kind of a magnitude kind of a value, So Vrms into Irms is called the apparent power, and it is having in units of volt into ampere. So volt into ampere, it's quite obvious, you are multiplying voltage and angle, and that's why you get apparent power. Why apparent power do we call apparent power? We'll see. Then we have P, so S times cosine part, so that is what we did. This theta is basically difference of angle, theta v minus theta I, which we did here, this one, okay, this part. So this theta is basically that. So P times cosine theta is now called real power, which we have already seen, and its its unit is watt. And the third one is called the reactive power, okay, which is called volt ampere reactive. So this reactive word is added to it, and that is called reactive power. So in fact, this, if you see, apparent power is something like which appears to be flowing in the circuit. So if you take the voltage and current and multiply as you do in case of a DC circuit, some power will be you will find, because that is basically multiplication of V and I. A similar thing if you do in a AC circuit, again you find that power, but it is called apparent power because it actually appears that that power is flowing, that much power is flowing, which is multiplication of Vrms into Irms. But this P cosine theta, that is, sorry, P S cos theta is called real power, because this is only the useful power which is delivered to the load. That is, this is the part which you can see as a heat if it is a resistor, okay. The other part is called the reactive power. You don't find coming out reactive power as a heat. Only this part is the useful power or the work power. And the second part, which doesn't come out, it is basically said to be stored in the circuit, and this is storage and is basically in form of exchange. The energy is exchanged from the source to load. So this energy actually is said to be flowing to the source and then back to the load, and that's why it is there, but it doesn't appear outside of it. It doesn't do any useful work, but it is inside the circuit, and it does some, it is there. It doesn't do any work for the outside world. So these are the three things which we have: apparent power, real power, and reactive power. This can also be seen in form of a power triangle. So if you have S here, if you multiply V and I and you get S here, then depending on theta you can find what is P and what is Q. So basically it is a right angle triangle where this is real power and this is reactive power, and then you have S, which is the apparent power, similar to the case when you had for what you had for Z. So Z means R here, and then X here, JX here, and this is Z. R plus R square plus X square is Z. That is the magnitude, and of course there is angle between Z and R. So that is what you call theta, and this is P. So if you have R plus JX as Z, then this angle appears as a power factor angle for the load. Now let us see actually what kind of real power is it, or the reactive power it is. So here if you see, I am taking a resistive circuit. So there is no in this ZL, only resistance is there, okay, and you have a AC being supplied to it, and therefore current also is AC. So if I take this V as Vt sine omega t, and It will be obviously in phase, there will be no phase difference if you have only resistance in this. So that is what is shown in this figure. So this is with voltage here, and this is current here, and if you see, there is no phase difference between voltage and current. And if you see, this is one cycle going from this point to this point, okay. Now when you multiply this V into I here, both are when both are positive and both are negative, the result is coming out to be always positive. And you shouldn't be knowing that whenever you multiply two sinusoidal quantities, then you get two sinusoidal quantities, then the frequency adds. Okay, so this is actually having same frequency. So if you see effectively, this is a sine wave. This v into I is also a sine wave. It is starting from this point and this point, where this is actually the for this multiplication part, that is the power part. Power part is this is the average, this is the part around which this multiplication happens, and this is again, if you see, is basically sinusoid. So the energy dissipated, that is V into I, is also sinusoid, and it is always positive. So it actually lifts up here. Okay, so there is some average part around which it is actually sinusoid. And the second thing you will find, it is having double the frequency. So up to this point, if you see, up to this point, from here to here, it is one cycle of power, and from here to here it is, here it is other cycle of power. So two cycles are there, whereas the current and voltages are having only one cycle. So that power oscillates here with twice the frequency, and it is actually having an average value. So this much amount of power is average or always flowing. Okay, and that is if you take this, it comes out to be V into I into cos phi, and it will always have a real part to it. You will not find any reactive part, because both are having this one. So if you go into this, take this representation, then this theta v and this theta v are going to be equal in case of a resistance. In case of a resistance, they are in phase, so this both the phases are same. So this is also theta v, and you apply here theta v, and this is theta v, so this is basically V into I RMS, and this is cos theta v is 1, this part is 1, and this part is again 0. So there is no reactive part when you have purely a resistive circuit. Okay, so when you have a purely resistive circuit, there will be no reactive part, and only real part, whatever is dissipated. So this is the amount of energy dissipated. This is actually, if you integrate this power, because multiplication of these two quantities will give you power, and when you integrate this power for suppose a cycle, and for a cycle, and then divide it by cycle, you will find that you get that what you call energy dissipated here. Now let us see what happens when you have purely an inductive circuit. Okay, so it is purely inductive now. This is I, and this is again. So if you see here, this is the voltage provided here, and in an inductive circuit, deliberately I have taken voltage from this point, starting from here, because I know that the current actually lags voltage by 90 degrees. Okay, current lags voltage by 90 degrees, so I have made the leading voltage beforehand, so that I can draw this figure from 0 point. Okay, so now if you find this is exactly 90 degree difference, phase difference between V and I, where I is leading. And if you multiply these quantities V and I along with angle of 90 degree between them, you can just see their multiplication here. And if you see the cycle, one cycle of voltage and current, or they are in same frequency. So if I take one cycle of current over here, from here to this point, this is one cycle. Then what about the power? Power, if you again see, it is oscillating with double the frequency. So they are actually, this is one cycle, whereas this is up to this point, is full cycle of I, whereas this is full cycle of power. So power is having twice the frequency, and if you see the average, if you take the average, because of this 90-degree phase difference, this average comes out to be 0. So what is seen here is this part is positive and the next part is negative. So in a cycle of power, this part is, you call it as energy absorbed, and this part is said to be energy returned. So this inductor actually absorbs some energy first in the say first half cycle, and in the second half cycle this again sends the energy to the source, and this continues. So effectively there is no energy going outside of the circuit. They remain inside the circuit. That is what the concept of reactive power is. You will find you don't find this coming out of the circuit, but according to this phasor multiplication, what we find is this is there in the circuit oscillating between source and the inductor here, and net power given out of the system is actually 0. So when you integrate this positive half cycle and negative half cycle over a cycle, you will find that the net power coming out is the net power is 0. So no power going outside of the circuit. So this is for a reactive power. So in this case there is no real power in fact. Okay, so if you go back to this, and this theta here is 90 degrees. So this part between this angle between this is 90 degrees, so this part becomes 90 degrees and the cosine part becomes 90 degrees, and therefore the real part is 0. In case of a inductor, purely inductor, the real part would be 0 and only reactive power would be there. You can guess what will happen for a capacitive circuit now. In a capacitive circuit, again, if you see, I am deliberately drawing I before, because I leads. So this is I beforehand, I have drawn it, and this is the current which actually this is the current which actually I'm sorry, the current actually leads, and the voltage here is drawn beforehand. This is voltage here, and the current is this one, and this is theta is equal to minus 90. So this time I think it is exactly opposite. I is at 0. Yes, it is plus theta there and it is minus theta, so it is starting back downwards here. Therefore there is a phase shift of 90 degrees and current is leading here. And again you find the same concept happening here, multiplying two sinusoidal quantities, having again the power is having double the frequency, but net power is 0 over a cycle. So the same thing is happening here, but this is for a capacitor. No power is being dissipated in a capacitor, so this gives you no power. This is 0. And what happens, though the current is flowing, voltage is there. Okay, current and voltages are there, but no power is seen outside of the capacitor. Where that power is going, if you measure by current and voltages here, you will find some power going into the capacitor, but that power doesn't appear outside of the circuit. What is happening? Basically that power is oscillating between the source and the capacitor, coming and going down, going out of the capacitor, and nothing comes out of the circuit. This happens in the circuit only. So that is how all the three things, that is all the power in the resistance, capacitor and inductors is actually happening. Now let us try to take one problem and see how we can see what happens here. Let us see, there are now we are talking things in terms of power, so we'll talk about power here. So here in this circuit you have a voltage source and there is one load which takes 2 kilowatt of power and has a power factor of 0.75. So power factor is basically the angle between current and voltage, V and I angle. So if you see, this is basically power factor angle between current and the voltage. And power factor, this is power factor angle, and power factor is basically cos theta, that is cos of theta v minus theta I. So basically what this question says is, there is one load which is taking real power, that is 2 kilowatt is the real power, and having a power factor angle of 0.75, and that is to be told that it is leading, so it is capacitive. Then load 2 is 4 kilowatt, power factor of 0.95, and it is lagging, so it is basically inductive. Now what is the, you have to calculate the overall power factor and complex power supplied by the source. So when I see from here, this point, I have to see what is the amount of power being supplied by it, because there are two loads here. So total power supplied by the source, and what is the total power factor angle, or total power factor, rather power factor seen by the source. So let us see. So if you have, let's say P1 is 2 kilowatt and power factor is given 0.75, so you can calculate the value of theta here, cos inverse 0.75, and that comes out to be minus 41, because it has been told that it is a leading power. So leading power factor means the current leads the voltage, so it is leading, so minus is put because we know that it is leading. So we can put again here, you can calculate the apparent power S for that particular this one, and now you can also calculate Q, because you know theta, so P and Q can be calculated. Q comes out to be negative here because this is leading power factor, and therefore you can calculate S as P1 plus JQ1. So this is the real part of S1, and this is the, so basically we have done nothing but we have tried to represent this power into a appropriate form of real and imaginary part. Once we know this power factor, that means angle is known. Power factor is basically giving you the idea of angle, and you know the real part. From that you can now generate the whole S from there. Similarly for load 2, the same process is being followed. You can generate S2, P2 plus JQT, and this comes out to be S2. Now this is the total amount of power which is to be supplied by the load, or which the load is actually supplying. So you just add them together and you find an interesting phenomena coming over here. I don't know if I can remove it here. Okay. So if you add this S1 plus S2, and find that it comes out to be, how come 6 is there? Okay, it is kVA. So this is basically adding here 2000, 6000, and this is basically subtracting. So the total amount of power is this much. That is basically 6000. You can multiply by 10 raised to power 3 because it is kVA. So 6000 kilowatt plus 449 kVA, and that is what you get. And from there you can calculate the value of power factor. Okay, so power factor can be calculated as cos theta. You can just divide them to get tan theta, or you can get P by S 6 by 1000 to get cos theta, the way you like. And this is the power factor you have for this particular circuit. So we'll stop here. Thank you.